Okay, let's take a minute to talk about the shape of molecules. This can be an important criteria. For example, if you're in the medicinal field, oftentimes the relationship between a molecule and its interaction with the body has to do with a receptor site. In other words, the shape of a molecule has to be correct, including the electron density, so that it fits into a receptor site and does what it needs to do. So let's take a moment to look at shape. This version you're going to get is not the full version, but it should be enough to give you an idea. We begin with the idea of where the electrons are. These are known as dot structures. If we ignore all of the interior electrons, we get a good blueprint of where the active electrons are in an element. Here we have the periodic table showing everything except the center region, which we can ignore for now. And we have between 1 and 8, this says 0, but it's really 8 valence electrons. They will spread themselves out such that for the group 1, you'll have 1 bonding electron. The group 2 will have 2 bonding electrons. These single electrons are bonding electrons. 3 will have 3 bonding electrons. 4 will have the maximum multiplicity. It's almost like they divide themselves amongst a square. But don't forget, we're dealing with 3 dimensions here. Therefore, this shape will actually be not square and flat, but rather tetrahedral, 109.5 degrees rather than 90. Try to think in 3 dimensions when you do this. 5 valence electrons, well, somebody's got to pair up. These things will be have 3 bonding electrons and a 4th region that occupies space but does not bond. Therefore, it's almost like a tetrahedron with one of the spots removed. Imagine that, and you end up with a trigonal pyramid. 2 lone pairs and 2 bonds will be like a tetrahedron with 2 spaces not available for bonding. We call this bent, with a bond angle of about 105 degrees. And here we have 3 lone pairs and only 1 bonding electron, so it'll have a linear shape right there. The noble gases don't bond at all. Okay, so why don't we take these single electrons and draw a line showing that they will bond to something. When we do that, we have hydrogen with its 1 line. All the other ones would be similar. But the 4 most common elements in the human body, and the ones that we're going to consider primarily, are hydrogen, oxygen, nitrogen, and carbon. Fortunately, they form 1, 2, 3, and 4 bonds respectively. Honk if you love chemistry. And there we are. There's oxygen with its 2 lone pairs and its 2 bonds, giving it that bent shape. Those 2 bonds can also come together like that, right? That's another possibility, giving it a linear shape. Let's consider nitrogen. Well, normally it would have its 3 bonding electrons and 1 lone pair, giving it a trigonal pyramidal shape, but 2 of those could come together to form a bent shape there, or all 3 could come together to form a linear shape. And with carbon, we have the maximum number of possibilities. Garden variety carbon will be tetrahedral, and the tetrahedron is shown there if you want to try to visualize it. Do you see that? There's your tetrahedron. If this is occupying space, it's now, imagine it just gone away. I'm putting my finger over it there. And that would make it trigonal pyramidal. Take away 2 and you have the bent shape. So these images here can help a little bit. Now carbon could spread out all of its 4 bonds like that, or it can do a 1 and another and a double bond. This would give it a trigonal planar shape like that. How about 3 and 1? It could do that as well. This will spread it out as like what we call an AB2 system. One thing with 2 things around it can go linear. They will always try to spread out as much as possible. And in fact, you can do a 2 and 2 combination. I don't think you can think of any others unless you're thinking of a quadruple bond, which has never been observed. And so we have a linear structure there. So carbon, not surprisingly, it's what we're mostly made out of, has all sorts of possibilities. And the big deal, of course, for these types of covalent substances is they can continue on ad infinitum, forever, so that they don't have to just be like salts, where you just are done after a plus combines with a minus. Okay, let's show some others. Here's sulfur. Now, normally you might think that sulfur, with its 6 valence electrons, would be similar to oxygen. Now, and I said I'd only give you an abbreviated version. I want to mention ever so briefly that once you get to the first, second, third shell, D electrons kick in, meaning that you can have extended octets leading to things like this, 2, 4, 6, 8, 10 electrons around it. But it's possible. I just wanted to allude to that. I hope that doesn't lead to too much confusion. The group 7s are known as the halogens, and they all tend to form one bond with the 3 lone pairs. Of course, it's true that weird things can happen once you get to the third block. We're not going to consider that, thank God. So chlorine will consider to primarily just form one bond with its 3 lone pairs. Now, there's, I think, one more. Yes, boron can form 3 bonds with its 1 lone pair. I include this briefly to point out that on occasion you can have what's called an incomplete octet. Most of these you'll see have their 8 electrons. If a line is 2 electrons, you'll see 8 almost always. These are incomplete. These can be extended. And these are actually normal because the first shell only needs its 2 electrons. See helium there. Fine. Okay. Think of these as tinker toys. Memorize some of them if you have to, and that's how they will come together to form molecules. I want to talk about the possibility of shape with molecules before we actually draw some. This analysis, which is sometimes referred ever so unfortunately as VESPER, or valence shell electron pair repulsion theory, just think of it as the shape of molecules, and think of it as something that's very logical. If you have an AB2 system, one thing in the middle with 2 things on the side, it can go linear, right? Therefore, the bond angle will be 180 degrees. If you have a flower that has 3 petals, well, things the most spread out they could possibly be is a triangle. We call this trigonal planar. The bond angles would be 120 degrees. But we've seen that things like here and like here, you have pairs of electrons which occupy space, but in essence we don't see them. That would be something like this, right? This would be an AB3 system, but one of them is a lone pair occupying space. So just cover that up and see the shape that results, and it's bent. This is very important because this one right here is an AB4 system where you have 4 things around a central atom. They could go tetrahedral. Notice that this is better than just flat. It's 109 degrees and as opposed to 90. So it's a real thing. It's something to try to wrap your head around. And if 2 lone pairs exist, well, that will be bent. And this is a really critical one because it's perhaps the most abundant substance on our planet. It's water. HOH with 2 lone pairs, right? HH. We'll take a look at that. Finally, if you have something that has 4 substituents, but one is a lone pair, just cover that up, and that's a pyramid. Do you see how it's a 3-sided pyramid? We call that a trigonal pyramid. That kicks in right here for singly bonded nitrogen. Okay, let's put it all together and draw some molecules, come up with their shapes, and there you go. I've selected these on purpose for this particular course because these will show up on assignments and on quizzes, so they're good ones to know. Here's methane. So we have an AB4 system, and carbon does tend to form 4 bonds. Remember, honk if you love chemistry. Hydrogen 1, oxygen 2, nitrogen 3, carbon 4. And let's just spread it out like that. What would be its shape and its bond angle? Well, an AB4 system is right there. It will be tetrahedral, bond angles 109.5, right there. Try carbon dioxide. And really, if you want to ace the test for this material, I'd recommend you do this again and answer these yourselves so that you have this memorized or at least figured out. Figured out would be better than memorized. Carbon dioxide. Well, we have AB2 system, and how would it make sense? Carbon tends to form 4 bonds and oxygen 2. Well, there's oxygen 2 like that, and here's carbon 4 like that. That would work out perfectly, wouldn't it, right? Every carbon has 4 bonds. Every oxygen has 2 bonds. Those 2 lone pairs go along for the ride. This looks very much like an AB2 linear system with bond angles 180 degrees. Carbon tetrachloride. Well, really, I mean, chlorine tends to form one bond, carbon tends to form four. We got all these lone pairs, but they're just going along for the ride. They're not affecting the shape, so it's entirely analogous to methane here, CH4. Tetrahedral with 109.5 degree bond angles. Let's do two more. Let's try ammonia. Oh, does it? There it is. I hope you didn't see that too long. Nitrogen tends to form three bonds. Hydrogen tends to form one, so they come together nicely. Don't forget that lone pair. So what's the shape? Four substituents, one of which you don't see. So it's like an AB4 system, but remove one, just let it occupy space. Trigonal pyramidal, and that lone pair apparently occupies slightly more space than a hydrogen atom, so the bond angle goes down by 2 degrees to 107. SO2 would be one of the most unusual ones. We're going to use this shape here and go ahead and draw it, and the oxygens fit perfectly in this variety, right? Two bonds, two lone pairs. There's sulfur. So I see an AB3 system, right? With one of them lone pairs. That sounds bent to me, just like it was trigonal planar, but with one of them taking up space. Bond angles 120 degrees. Last one, BF3. Before I do it, I didn't draw it, but please consider the water molecule. And draw it if you need to, and I hope you come to the conclusion that it would have a bent structure with a bond angle of about 105 degrees, right? Each lone pair is slightly bigger than a hydrogen atom. Okay, boron trifluoride. Boron tends to form three bonds. Fluorine tends to form one. We're good to go. One thing I should point out is I didn't draw them because it took too much time, but we should have three lone pairs on each of those chlorine atoms. See them? Okay, so boron trifluoride, that's just a simple AB3 system. Don't be confused thinking it's 90 degrees here. An AB3 system can spread out to form 120 degree bond angles with a trigonal structure. This is an introduction to shape.